Okay, this is my solution for the problem that we did Wednesday of week 4. And this was our first introduction to friction, but we started off with just practicing without friction. And there's a box, cold box on ice, and it's being pulled across the ice. It's being pulled across the ice with some tension. So there's a force of tension, and the box is accelerating with some known acceleration. So as we talked about this problem, we discovered that this part of the problem is useful in order to figure out the mass of the box. So let's show how that works. So here's the box, and now we'll draw a free body diagram. So there's the force of gravity downward, the normal force upward, and the force of tension goes this way. And so we'll choose axes, x and y, and write down that the sum of the forces in the x direction, the sum of the forces in the y direction, are equal to the mass times the acceleration in those directions. So it doesn't leave the ice. The sum of the forces there is 0. And the sum of the forces in the x direction is just mass times its known acceleration, where the acceleration is 1 meter per second squared. So in the x direction we have the force of tension. In the y direction we have the normal force and gravity downward. Turns out that that's actually not so necessary for finding the mass, because we were told that the force of tension is, let's see, 2 newtons, and the acceleration is 1 meter per second squared, so this is 2 kilograms. Okay. After that, then, the box is on carpet. So when the box is on carpet, now we have to think about friction. And we still have a force of tension, but now when we draw the free body diagram, there's the normal force, as usual, the force of tension, and mg. And this time now, there's some unknown force, which turns out to be the force of friction. So, okay, we do the same thing. We choose axes, x and y, and the sum of the forces in the x direction and the sum of the forces in the y direction, once again, will be ma and 0. Now the acceleration is either given or 0, which I guess is another way of being given, but anyway. And so when it's 0, we call that static, and when it's not 0, or when it's moving, even with constant speed, we call that kinetic. So we had several different examples given in the problem of combinations. But anyway, let me finish going here. So we have the force of tension positive and the force of friction, and then we have the normal force and mg. Okay, so that means that the mystery force, the force of friction, was going to be the force of tension minus ma. So I'll write that down. The force of friction is equal to the force of tension minus ma. Okay, so we can make a table. So let's start a new page here. We can make a table, and the table looks something like this. That it was the force of tension, and it was the acceleration of the block, and then the force of friction. Okay, and we were given that with 2 newtons of force, it doesn't slip. And with 3 newtons of force, it doesn't slip. With 4 newtons of force, it goes from not slipping to slipping. And after it slips, it's accelerating at 1 meter per second squared. At 5, again, you have 1.5 meter per second squared, and at 6 newtons of force, you have 2 meters per second squared. Okay, so the force of friction is going to be the force of tension minus MA, where M is 2 kilograms. Okay, so when acceleration is 0, the friction force is just the force of tension. So 2 newtons, and 3 newtons, and 4 newtons. Now, after it accelerates, then it's going to be the tension minus MA. So at 1 meter per second squared times 2 kilograms, that's 2 newtons. So we have 4 newtons minus 2 newtons is 2 newtons. Then we have 5 newtons minus, 2 kilograms, I'll write it out, times 1.5 meters per second squared. So that's 3 newtons, so that's still 2 newtons. And then 6 newtons minus 2 kilograms times 2 meters per second squared, which is 4, so it's 2 newtons. And what we found here is that as we applied a force, the friction force increased linearly so that it was equal to, so this is a slope of 1 here, to some point when the friction breaks, the static friction is overwhelmed, and it's then flat all the way out. And we said that this point right here is proportional to the normal force, and all of these points here is mu k times the normal force. So static friction has a maximum, and kinetic friction stays constant. So you should notice in this particular problem that we can find from the previous page that the normal force is equal to mg. So the force of static, or the coefficient of static friction, is equal to the maximum that the friction can provide, static friction, which was 4 newtons. So the max all over the normal, 4 newtons, divided by the normal force, which was 20 newtons, using 10 for the acceleration due to gravity. So 4 over 20 is, 0.2. Has no units, it's just a dimensionless parameter. Mu k is any of these, force of kinetic friction divided by the normal force. So 2 newtons divided by 20 newtons, which is just 0.1. And you should note that mu k is less than mu s. And this is a very general trend for kinetic friction and static friction. So you'll notice that when you overcome static friction, things leap in a hurry, and that's because the coefficient of kinetic friction is typically less. Okay, great problem. Thanks.